Okay, so welcome to Statistics for Psychology. And I know what you're thinking. You're thinking, great, math, formulas. This is going to be painful, and I'm just going to memorize enough to pass and then forget it all. And look, I understand that. I do. Statistics is often taught in this unbelievably dull way where you just learn to plug numbers into equations and calculate things without ever understanding why you're doing it or what any of it means. But here's the thing, and I need you to understand this right at the beginning because it's going to frame everything else we do. Statistics is not just mathematics applied to data. It's not. It's something deeper than that. It's a set of tools, conceptual tools, hard-won over centuries, that human beings develop to protect themselves from their own pathological tendency towards self-deception. Okay, and that's no joke. You are going to be psychologists, or at least that's presumably why you're here. And if you're going to be a psychologist, you're going to make claims about the human mind. You're going to sit across from people who are suffering, people who are confused, people who are desperate, and you're going to say things that they will believe. And they'll believe you because you have credentials, because you're the expert, because they're lost and you're supposed to know the way. And so the question is, what do you actually know? And how do you know it? And how do you know that you're not just wrong? Because you can be wrong, you can be catastrophically wrong. And the history of psychology is littered with people who were wrong in ways that destroyed lives. And they weren't stupid people, they weren't evil people, they were often brilliant, well-educated, well-intentioned people who were absolutely certain they were helping, and they weren't. All right, so let me tell you a story, and it's a terrible story, but you need to hear it. So in 1935, a Portuguese neurologist named Egas Moniz developed a procedure called the prefrontal leucotomy. You know it as the lobotomy. The idea was simple, roughly speaking. There are patients who are agitated, anxious, psychotic, they're unmanageable, and if you go in and sever the connections between the prefrontal cortex and the rest of the brain, they calm down. And they did calm down, that was true. They became docile, manageable, and Moniz looked at this and thought, I found something and this works. In 1949, he won the Nobel Prize in Medicine. The Nobel Prize. Now think about that. This is the highest honor the scientific community can bestow. This is the world saying, yes, this is a breakthrough. This is genuine progress, in the alleviation of human suffering. And what actually happened? What actually happened is that tens of thousands of people, so an estimated range somewhere to 40 to 50,000 people in the United States alone, had ice picks, literally ice picks, driven through their eye sockets and into their brain. That was the ice pick lobotomy developed by Walter Freeman, who became kind of evangelist for the procedure. He traveled around the country in a van he called the lobotomobile, and that's real, that's not a joke, performing lobotomies in state hospitals and psychiatric institutions on people who were depressed, on people who were anxious, on people who were difficult teenagers or moody women. One of his patients was Rosemary Kennedy, JFK's sister. She was 23 years old, described as moody, rebellious, and they lobotomized her. She spent the rest of her life, the next 63 years, in an institution, unable to speak coherently, incontinent, and with the mental capacity of a 2-year-old. And Freeman wasn't a monster. That's what you have to understand. He genuinely believed he was helping. He had clinical intuition. He saw patients who were suffering. He did the procedure. And in the short term, in the immediate aftermath, many of them seemed better. They were calmer. They were more manageable. And he concluded that it worked. Okay? But it didn't work. It destroyed people. It destroyed their personalities, their capacity for complex thought, their humanity. And no one knew because no one was measuring properly. No one had control groups. No one was doing long-term follow-up with validated instruments. They were trusting their clinical impressions. And their clinical impressions were wrong. Okay, you might think, well, that was the 1940s. Okay, we know better now. That couldn't happen today. Oh, but it can, and it did. So let me tell you about recovered memory therapy. In the 1980s and into the 1990s, there was a movement in psychotherapy based on an idea that seemed plausible and that seemed helpful, that many psychological problems, especially in women, were caused by repressed memories of childhood sexual abuse. The theory was Freudian, roughly speaking. Traumatic memories are pushed into the unconscious and they fester there, causing depression, anxiety, eating disorders, relationship problems. And the cure was to recover these memories, to bring them back into consciousness and to confront them. And so therapists started using techniques, hypnosis, guided imagery, suggestive questioning, to help patients remember abuse that they had supposedly forgotten. And the patients did remember. That's the thing. Under these conditions, they produced vivid, detailed, emotionally compelling memories of being abused, and sometimes by parents, sometimes by relatives, sometimes by satanic cults. And yes, that was a thing, the satanic ritual abuse panic. Patients remembered being forced to participate in rituals, and sacrifices and things that were so horrific. I'm not even going to describe them here. And the therapists believed them. And why wouldn't they? The memories were so detailed. The patients were so certain. And the theory predicted exactly this, that these memories would be repressed and would need to be excavated. Except it wasn't real. The memories were false. They were constructed, what we call confabulated, through the therapeutic process itself. The techniques that therapists were using didn't recover memories. They created them. And we now know this because cognitive psychologists like Elizabeth Loftus did actual research. They did controlled experiments. They demonstrated that you could implant false memories in people's minds, vivid memories of events that never happened, using exactly these kinds of suggestive techniques. But before we knew that, before the data came in, thousands of families were destroyed. People went to prison. Parents were accused of monstrous crimes by their own children, crimes that never occurred. Some of these people died in prison. Some committed suicide. And the therapists were certain they were helping. They had years of clinical experience. They had case studies. They had patients telling them with tears streaming down their faces, yes, this is what happened to me. They had intuition. Okay? And they were wrong. They were doing harm on an almost unimaginable scale, and they didn't know it. And they didn't know it because they weren't measuring. They weren't comparing outcomes. They weren't testing their assumptions against reality in any rigorous way. There is a line by Feynman, Richard Feynman, the physicist, and I think it might be the most important sentence ever written about science. He said, the first principle is that you must not fool yourself, and you are the easiest person to fool. You are the easiest person to fool. You sitting here, intelligent, educated, well-meaning, you are so easy to fool. Your own perceptions will lie to you. Your memory will lie to you. Your intuitions, which feel so certain, so trustworthy, will lead you into error after error after error. And this isn't a flaw in the sense that it can be fixed by just trying harder or being more careful. This is how human cognition works. We evolved to make fast decisions in dangerous environments. We evolved to see patterns even when they aren't there. We evolved to construct narratives, to confabulate, to fill in gaps with plausible sounding nonsense. We evolved to protect our beliefs from contradictory evidence because changing your beliefs is metabolically expensive and socially dangerous. And the cognitive biases aren't bugs, they're features. They kept your ancestors alive long enough to reproduce, but they make you a terrible scientist if left unchecked. Let me walk you through some of the major ways your mind deceives you because you need to know your enemy. Confirmation bias is the tendency to notice, seek out, and remember evidence that supports what you already believe, while ignoring, dismissing, or forgetting evidence that contradicts it. Think about how you process political news. If you lean left, you probably find conservative arguments obviously flawed and liberal arguments persuasive. If you lean right, it's the opposite. But here's the thing. Neither of you is evaluating the arguments objectively. You're both filtering the world through your pre-existing beliefs. This happens automatically. You don't decide to ignore contrary evidence. You literally don't see it. Your attention is drawn to confirming information. Your memory encodes it more strongly. When you recall evidence later, you remember what fits your beliefs and forget what didn't. So now think about what this means for research. A researcher has a hypothesis they believe is true. That's often why they're studying it. They run a study, they collect data, they analyze it. At every step, confirmation bias can creep in. Which observations do they pay attention to? Which results do they emphasize? Which analyses do they run? If the human mind is biased towards confirming beliefs, then researchers who are human are biased toward confirming their hypotheses. This is why we need formal procedures. This is why we need statistics. Not because statistics is fun, obviously, but because without it, we're at the mercy of our own biases. The availability heuristic is the tendency to judge probability based on how easily examples come to mind. What's more dangerous, flying or driving? Most people think that flying is scarier, more dangerous, but statistically, driving is far more deadly. Per mile traveled, you're orders of magnitude more likely to die in a car than a plane. So why does flying feel more dangerous? Because plane crashes are vivid, dramatic, heavily covered by media. When a plane crashes, you hear about it for weeks. You can easily bring examples to mind. Car accidents are routine, unremarkable, not memorable. You can't easily bring examples to mind. Okay? Your brain uses availability, how easily examples come to mind, as a proxy or a shortcut for frequency. Vivid, memorable events seem common. Routine, forgettable events seem rare. But the vividness is not the same as frequency. You have it exactly backwards. The rare, vivid events feel likely, whereas the common, mundane events feel unlikely. Think about how this affects clinical practice. A therapist sees a patient who reminds them of a previous case that went badly. That vivid memory makes them overestimate the probability that this patient will also go badly, and they might recommend more aggressive treatment than is actually warranted. The availability of a memorable example distorts their judgment. Statistics provides the correction. Instead of relying on what comes to mind, you count, you measure, you compare actual frequencies. The numbers don't care what's vivid. So here's another one. Your brain is a pattern detection machine. It's spectacularly good at finding patterns. So good that it finds them even when they aren't there. Okay. Look at clouds, okay, and you see faces. Look at random noise or listen to random noise and you hear words. Look at stock charts and you see trends that will continue into the future. Look at random events and we see meaningful sequences. This was useful for our ancestors. It's useful for us. If you thought you see a predator in the bushes and you're wrong, you just lost a few seconds. If you failed to see a predator that was actually there, you died. So evolution built us to err on the side of caution, of seeing patterns, even if many of them are false positives. But in the modern world, this bias is dangerous. We see causal connections and coincidences, and we see trends and random variation. We see evidence for our theories in the noise. A patient takes an alternative medicine and feels better. Was it the medicine, or would they have felt better anyway? They see a pattern, medicine, then improvement, and they infer causation. But correlation or association is not causation. The pattern might be coincidence. So statistics gives you tools to distinguish real patterns from noise. It asks, how likely would this apparent pattern be if nothing real were going on? If the answer is very likely, maybe you're just seeing noise. If the answer is unlikely, maybe the pattern's real. So what's the solution to all of this? Okay, what do you do when you know your own mind is unreliable? The solution is discipline, external discipline, a set of methods and procedures that force you to confront reality whether you want to or not, that constrain your natural tendencies towards self-serving interpretation, okay, that makes you check. That's what statistics is. That's what the scientific method is. It's not just a way of finding things out. It's a way of protecting yourself from yourself. When you run a controlled experiment, you're not just gathering data, you're preventing yourself from seeing illusory patterns, illusions. The control group exists because without it, you will attribute every improvement to your treatment, even if the improvement would have happened anyways, just coincidentally. So when you calculate a confidence interval, which we'll talk about later, you're forcing yourself to acknowledge uncertainty because your intuition wants to be certain. Your intuition wants to say, I know this works. And a confidence interval says, here's the range of values that are actually consistent with your data. You don't know as much as you think you know. When you do a power analysis, which we'll talk about, before running a study, you're checking whether your study is even capable of detecting an effect if one exists. Because if your sample is too small, you might miss real effects. Or worse, you might find significant results that are actually just noise, just fluctuations in the data that happens across an arbitrary threshold. So this is what we're going to learn in this course, not just how to calculate things, but why we calculate them, what each technique is for, what error it protects against, what happens when you don't use it. Okay. All right, now that you understand why statistics matters, why it's not just a technical requirement, but actually a moral necessity, let's talk about what statistics actually are. Let's get into the substance. Because you need the philosophy, but you also need the tools, okay? The philosophy without the tools is just hand-wringing. It's just, worrying about anxiety. The tools without the philosophy is just blind calculation. You need both. So let's start with the basic definition. What are statistics? And I mean this technically. What are they precisely? So statistics are numbers used to describe data from a sample. That's the definition. Numbers used to describe data from a sample. Now that definition has some terms in it that we need to unpack because each of those words carries weight. But before we get into those technical details, I want you to notice something about this definition. Statistics are numbers used to describe. They're descriptive. They're summaries. They take something complicated, a whole collection of data, and reduce it to something simpler that you can communicate. And that's both their power and their danger, okay? Their power is that they let you grasp something that would otherwise be overwhelming. If I give you 1,000 numbers, you can't hold them all in your mind. You can't see the pattern. You can't understand what's going on. But if I give you a summary, an average, a measure of spread, a relationship, suddenly you can grasp it. You can think about it. You can compare it to other things. Their danger is that in the process of summarizing, you lose information. The summary is not the data. The map is not the entire territory. And if you forget that, if you treat the statistic as if it were the complete picture, you will be misled or mislead others. We'll come back to this, but I want you to hold it in mind from the beginning. Every statistic is a simplification, and every simplification involves choices about what to keep and what to discard. And those choices matter. They have consequences, and they can be made well or badly, honestly or dishonestly. Now let's talk about populations and samples because this distinction is fundamental. It's the basic mechanism that makes statistics work. A population is every example or member of a group that you're interested in making a statement about. Think about what that means. A population is the complete set, the whole thing, every instance of whatever you're studying. In psychology, This often means a group of people. If you're interested in understanding depression in adults, your population is all adults who have depression. If you're interested in understanding how children learn language, your population is all children. If you're interested in making a statement about the discrepancy in mental health disorders between men and women, then your population would be all men and women, okay? Now here's the problem. You almost never have access to the whole population. So let's say you want to understand the mental health of college students in America. That's your population, all college students in America. How many is that? About 20 million, give or take? Are you going to survey all 20 million of them? Are you going to give psychological assessments to each one? Of course not, okay? You don't have the time, you don't have the money, you don't have the access. It's simply not possible. So what do? You take a sample. A sample is a selection of some of the members of the group that you're interested in making a statement about. You can't study all 20 million college students, so you study 100 or 1,000 or 5,000. Okay, you take a subset, a piece of the population, and you study that piece in detail. Okay, and this is where the magic happens. Okay, this is where statistics does something remarkable, and also something that can go terribly wrong if you're not careful. So you study a sample, a small piece, and from that sample, you make inferences about the whole population. You learn something about 1,000 people, and you use that knowledge to draw conclusions about 20 million, okay? So take a look at this chart here, the circles, okay? Look at this. You have an entire population, all the people you care about in your study, and you have a sample, a small subset of those people. You measure your sample, you calculate statistics from your sample, and then you use the statistics to infer what's true about the broader population. That's the fundamental logic of statistical inference. You go from the part to the whole, from the particular to the general, from what you can observe to what you cannot observe. Okay, now think about how extraordinary this is, and also how dangerous. You're making claims about millions of people based on a study of a few thousand, or maybe even 100 or 50. How can that possibly work, and when does it fail? The answer is it can work, but it's not guaranteed. And that's crucial. You can never be certain that what's true in your sample is true in the population. There's always a chance that your sample is unusual, unrepresentative, different from the population in important ways. But, and this is a key insight, you can quantify that uncertainty. You can calculate how likely it is that your sample is misleading. You can put numbers on your doubt. And that, in a sense, is what statistics does. It doesn't eliminate uncertainty, but it makes uncertainty precise. We'll spend much of this course learning how to do that, but I want you to understand right from the beginning that statistics is fundamentally about making inferences from samples to populations and about being honest about the uncertainty involved in those inferences. Before we go further, let me introduce you to some notation, okay? Because we need a common language, and this isn't just pedantry. The symbols remind us of distinctions that actually matter. These are important, okay? So pay attention. So for the size of a population, we use capital N, big N, okay? The whole thing. For the size of the sample, we use little n, okay? Lowercase n, the subset. This notation carries meaning. When you see a capital N, you should think this is about the entire population. When you see a lowercase n, you should think this is about a sample. The symbols are shorthand for a concept, and the concept is important. Now, there's another crucial distinction. When we calculate a summary number from a sample, we call it a statistic. When referring to the same kind of number for an entire population, we call it a parameter. This is a fundamental distinction. Statistics comes from samples. Parameters describe populations. Here's an example, okay? The mean, the average of a sample is symbolized with an X bar, okay? That's the sample mean. It's a statistic. But the mean of a population has a different symbol, the Greek letter mu. Mu is the population mean. It's a parameter. So why different symbols? Because they're different things. The sample mean is something you can calculate. You have the data, you add up the numbers, you divide by how many there are. The population mean is something you're trying to estimate. You don't have all the data. You're inferring it from your sample. The sample mean is known. The population mean is unknown. You use the known to estimate the unknown. And the gap between them, the difference between what you know and what you're trying to know, is where all the interesting statistics happens. We'll use different symbols throughout the course to distinguish parameters from statistics. It might seem like a small thing, but it's not, okay? It's a constant reminder that there's a difference between what you've measured and what you're concluding, between the evidence you have and the claim that you're making. So make sure you memorize those. Okay. So now that we understand the basic relationship between populations and samples, we can talk about the two major branches of statistics. These are different kinds of activities and they serve different purposes. The first branch is descriptive statistics. Descriptive statistics are, as the name suggests, used to summarize and describe a group of numbers from a research study. So when you calculate an average, you're doing descriptive statistics. When you calculate a standard deviation, you're doing descriptive statistics. When you create a graph or a chart, you're doing descriptive statistics. Okay. The goal of descriptive statistics is to take a collection of data and make it comprehensible, understandable, to reduce the complexity and extract the essential features, to communicate what the data looks like, to summarize it. Okay, the first several topics in this course are going to focus on descriptive statistics. We'll learn how to describe the center of a distribution, what's typical, what's average. We'll learn how to describe the spread, how much variation there is, how different the observations are from each other. We'll learn how to visualize data in ways that reveal patterns and relationships. Okay, but here's the thing about descriptive statistics. They only tell you about the data you have. If you've collected a sample, descriptive statistics tells you about that sample. They don't, by themselves, tell you anything about the population. To make claims about the population, you need the second branch, inferential statistics. Inferential statistics are used to draw conclusions and make inferences based on the numbers from a research study. They're the bridge from sample to population. They're how you go from what you've observed to what you haven't observed. Inferential statistics also rely on probability, and we'll get to that later. They ask questions like, if the drug doesn't really work, how likely is it that I would have seen results this strong? If there's no relationship between these variables, how likely is it that I would have found a correlation? We'll spend the second half of the course on inferential statistics. So you'll learn hypothesis testing, which is a formal procedure for deciding whether your evidence supports your claims. You'll learn about p-values, confidence intervals, statistical significance. You'll learn how to quantify uncertainty. But even though we're covering these topics sequentially, I want you to understand that they're connected. Descriptive statistics tell you what you found. Inferential statistics tells you what it means, whether it generalizes beyond your sample. And you need both. Description without inference leaves you with a pile of facts that don't connect to anything larger. Inference without description leaves you making claims that you can't support. So the two branches work together. So we've established what statistics are and how they're organized, but let's step back and ask the more fundamental question. Why do we do this at all? What's the point? The answer is that statistics helps us to answer empirical questions. Okay. Now, what is an empirical question? An empirical question is a question that can be answered by observation and evidence. It's a question about the world, about how things actually are, rather than a question about logic or values or definitions. Empirical is another word for scientific. What is the capital of France is not an empirical question in the relevant sense. It's a matter of definition and convention. Do people who exercise have lower rates of depression is an empirical question. It's asking about a pattern in the world that you could, in principle, investigate by gathering data. Okay, so science is fundamentally about answering empirical questions. And psychology is a science, or at least it aspires to be. So psychology is about answering empirical questions about the mind, about behavior, about human nature. Okay, so think about the questions psychology tries to answer. Why do we dream? What causes depression? Does therapy work? Are there real differences between men and women in how we think, our cognitive abilities? Does social media affect mental health? Why do people become addicted? What makes some people more resilient than others? These are empirical questions. They have answers, maybe complex, maybe partial, maybe uncertain, but answers that exist in the world and can be discovered through careful investigation. That's empirical, okay? But here's the problem. The world doesn't just hand you the answers, right? Reality is complicated. Effects are often small, variables are, tangled up, causes are multiple, and they interact in complex ways. Your intuitions are unreliable, your perceptions are biased. You can't just look at the world and see what's true, okay? You have to do the work of careful measurement, systematic observation, rigorous analysis. You have to gather data, calculate statistics, test hypotheses. And that's what this course is about. It's about giving you the tools to answer empirical questions, not just in psychology, but in any domain where science and evidence matters, okay? Now, I want to be honest with you about something. I feel like I keep underselling statistics a little because what I've said so far makes it sound like statistics just gives you answers. Put in the data, get out the truth. But it's not that simple, unfortunately. Statistics has limitations. They take time to work. Even when you have good evidence, building scientific knowledge is slow. It can be uncertain. We don't prove things in statistics. We don't say that anything is definitely true. We say we have evidence. We say our hypothesis appears to be supported. We say the data are consistent with a particular interpretation. This tentativeness in our language, this uncertainty, it's not a weakness, it's honesty, it's intellectual integrity. It's acknowledging the limits of what we can know. So as we go through this course, I want you to become comfortable with this kind of language. Instead of saying X causes Y, you'll learn to say our data suggests a relationship between X and Y. Instead of saying we proved our hypothesis, you'll learn to say we found evidence consistent with our hypothesis. This is what it means to think statistically. It means holding your conclusions lightly. It means being aware of uncertainty. It means not claiming more than your evidence supports. Okay. All right. Let me make this concrete. I want to walk through some actual research scenarios, the kind of studies that psychologists conduct, the kind of questions statistics helps us answer. So for each one, I want you to pay attention to several things. What's the question? What's the population? What did the researchers find? And most importantly, what can we conclude and what can't we conclude from the results? Okay. I also want you to make predictions. So before I tell you the results, I want you to think about what you expect. This is the beginning of scientific thinking, generating hypotheses based on what you know and then checking them against reality. All right, example 1, the attractiveness of defendants. So here's our first scenario. A legal psychologist, and yes, that's a real thing, psychologists who study how psychological factors influence the legal system, wanted to investigate whether the physical attractiveness of a defendant affects jury decisions. So think about this for a moment. We have a legal system built on the principle that people should be judged fairly, based on the evidence of what they did, not on irrelevant characteristics. Lady Justice is blindfolded for a reason, right? But human beings aren't perfectly rational. We're influenced by all sorts of factors we shouldn't be influenced by. Could attractiveness be one of them? Here's how the study worked. The researcher had participants read court transcripts from a trial and then give their verdict regarding the defendant. The transcripts were identical. The evidence was exactly the same. The crime was the same. Everything was held constant, except for one thing, the photo attached to the transcript. So 100 participants saw a photo of the defendant made up to look attractive. Another 100 participants saw a photo of the same defendant made up to look unattractive. Same person, same case, different appearance, okay? So we have a sample of 200 people. That's our lowercase n equals 200, divided into two groups of 100 each. And we're asking, will the attractiveness manipulation affect the verdicts they give? Now, before I tell you the results, I want you to make a prediction. What do you think happened? Do you think attractiveness influenced the verdict? Most of you probably have an intuition here. You might think, of course it matters. People are biased. Attractive people get treated better. Or you might think, no, this is a serious legal context. People will be objective. They'll focus on the evidence, okay? Notice what you're doing when you're making a prediction. You're generating a hypothesis. You're saying, based on what I know about human nature, I expect this result. And that's the beginning of science, having an expectation and then checking it against reality. So here are the results. Of the 100 participants who saw the unattractive photo, 73 gave a verdict of guilty. Of the 100 who saw the attractive photo, 37 gave a verdict of guilty. Think about that. 73% versus 37%. Nearly twice as many guilty verdicts for the unattractive defendant as for the attractive one. Same crime, same evidence, same transcript. The only difference was the photograph. And that difference corresponded to a massive difference in verdicts. Now, what does that tell us? Okay, first, it tells us that our legal system may have a serious problem. If jurors are influenced by attractiveness to this degree, if they're more likely to convict people who are less attractive, then justice is not being administered fairly. People are being judged in part on something that has nothing to do with their guilt or innocence, okay? This is exactly the kind of thing we talked about at the beginning. Remember the lobotomists? They had intuitions. They thought they knew what was helping patients, but they weren't measuring. Here, we're measuring, and the measurement reveals something disturbing about human judgment. Second, it tells us something about human psychology more broadly. We are influenced by factors we shouldn't be influenced by. We like to think we're, objective, rational, logical, fair, but we're not. Our judgments are contaminated by biases that we don't even know are there. Third, and this is where statistics comes in, it tells us that we can study these biases. We can detect them. We can quantify them. Without this kind of research, we might never know that attractiveness affects legal judgments. And we might have suspicions maybe, but no evidence. Statistics gives us the evidence, okay? But let me also point out what we can't conclude from this study, because this is equally important. We cannot conclude that this happens in real courtrooms with real defendants in front of real juries. This was an artificial setting. Participants were reading transcripts, not sitting in a courtroom. The defendant wasn't real. The stakes weren't real. Maybe in actual trials with actual consequences, people would be more careful, okay? We cannot conclude that attractiveness is the only factor or even the most important factor, okay? Many things influence verdicts. So this study isolated one variable, but in the real world, many variables operate simultaneously. So we can't conclude that attractiveness caused the difference in a simple, direct way. There could be mediating factors. Maybe attractiveness affects how trustworthy someone appears, and trustworthiness affects verdicts. The mechanism might be more complex, than a direct effect. And this is what it means to think critically about research. You take findings seriously. This is real evidence of a real phenomena, but you also recognize the limitations. You don't overclaim. You hold your conclusions lightly. Okay, let's try another example. This one is from health psychology. So, a health psychologist wanted to know whether owning a pet affects health, which is why I have cats in this PowerPoint. Okay, this is the kind of question that matters to people. Should I get a dog? Should I get a cat? Will it make me healthier? Will it make me happier? And it's the kind of question that science can and has addressed. Okay, so here's the study design. The researcher recruited 100 residents of one floor of a retirement home. 50 of them were given pet cats to take care of. The other 50 were not given pets. Then the researcher counted the number of doctor visits by each resident over the course of a year. So we have a sample of 100 people divided into two groups, pet owners, non-pet owners, and we're comparing a health outcome, doctor visits. Again, before I tell you the results, make a prediction. Do you think pet ownership will be associated with better or worse health, more or fewer doctor visits? You probably have some intuition here too, okay? Many people believe that pets are good for you. They provide companionship, they give you a reason to get up in the morning, they reduce loneliness. Maybe having a cat to care for makes these elderly residents healthier. Or maybe you're skeptical. Maybe you think a cat, how much difference could a cat make? Maybe a dog, but a cat? These are elderly people, in a retirement home. Their health is determined by much bigger factors than whether they have a cat. Maybe it's just not enough to make an impact. Okay, so here's what the study found. Non-pet owners made twice as many visits to the doctor during the year as pet owners. Twice as many. That's a substantial difference, okay? Now, what should we make of this? On one level, it's consistent with the hypothesis that pet ownership improves health, right? People with pets went to the doctor less. That's good news for pet lovers. It suggests there might be, real health benefits to animal companionship. And I'll be honest, I like this result. I have a dog, okay? I have a farm. I have lots of animals. So I'd like to believe that having a dog is good for me. Maybe you have a pet you love and you think, yes, of course, it contributes to my well-being, obviously. But wait, this is exactly where we need to be careful. This is where our biases can lead us astray. We want to believe this result, so we're tempted to accept it uncritically. But think about the design of the study. Think harder. What are some alternative explanations? Maybe the people who agreed to take care of cats were healthier to begin with. Maybe only the healthier residents felt up to having a pet. If so, the cats didn't cause better health. They were just associated with pre-existing health. Okay? Maybe having a cat gave people reason not to go to the doctor. If you have a pet depending on you, maybe you're reluctant to leave. That would look like better health in the data, but it wouldn't actually be better health. It would actually be worse health. Maybe the act of caring for something, having a purpose, a routine, a responsibility is what actually matters. And it could be anything that gives you that, not specifically a cat. Maybe a houseplant would work just as well. Okay, see what we're doing here? We're considering alternative explanations. We're asking what else could account for these results. And this is crucial. This is what separates good thinking from bad thinking. Okay. The study found a correlation between pet ownership and fewer doctor visits. Yes, correlation means the two things are related. They go together. But correlation does not mean causation. Just because two things are related does not mean that one causes the other. This is one of the most important lessons in statistics or in psychology in general, and we'll come back to it many times throughout this semester. So for now, just remember, when you see a relationship in data, always ask yourself, what else could explain it? The obvious interpretation is not always the correct interpretation. All right, last example. One more example, and this one touches on something that might be relevant to those of you considering professional careers. A social psychologist was concerned that law schools were producing lawyers who were more interested in winning than in ethics and what was right, that they were no longer teaching ethics, and they were more concerned with winning cases. The researcher wanted to know, are lawyers more competitive than other people? So here's what they did. They gave a competitiveness rating scale to 100 lawyers and 100 non-lawyers, and this scale measured how competitive people were, how much they wanted to win, how much they valued victory over other outcomes, and the scale went from 0 to 80, higher scores meaning more competitive. Okay, what do you think they found? Think about it. So you might have strong opinions about lawyers. Okay, stereotypes exist for a reason sometimes. Lawyers are supposed to be argumentative, aggressive, competitive. That's the image anyway. Some people have a gut reaction to lawyers. They have preconceived notions based on experiences, observations, TV shows, whatever. So here are the results. Lawyers averaged 68 out of 80 on the competitiveness scale. Non-lawyers averaged 47 out of 80. That's a substantial difference. Lawyers in this sample were considerably more competitive than non-lawyers. Okay, what does this mean? Well, it suggests that there might be something to the stereotype. People who become lawyers really are more competitive on average than people who don't. This could matter for all sorts of things, how they approach their work, how they interact with clients, how they behave in negotiations. But again, let's think critically. Does law school make people competitive, or do competitive people choose to go to law school? This is the selection effect. Maybe law school doesn't change anyone. Maybe it just attracts people who were already competitive in the first place. If you're highly competitive as a young person, you might be drawn to a profession that's about winning arguments. The profession isn't causing the competitiveness, it's attracting it. Or maybe it's both. Maybe competitive people are drawn to law, and then law school makes them even more competitive. The truth might be some combination of selection and socialization. The point is, the data alone can't tell us. We need to think carefully about what processes could produce the pattern that we observe. Okay? I want to draw an analogy here because I think it's illuminating. Okay? There's a symbol that appears in legal context, the scales of justice. You've probably seen it. Two pans hanging from a balance beam. The idea is that evidence is weighed on both sides, and the side with more weight prevails. Okay? There's also a symbol used in psychology, the Greek letter psi. You see it on textbook covers, on department logos. And here's what I want you to see. Statistics operates in both domains in a similar way. Statistics is about weighing evidence. It's about determining which interpretation is better supported. It's not, it's about not jumping to conclusions based on insufficient data. Okay, and like the legal system, statistics operates on a principle of innocent until proven guilty. When you do research, you start with what's called a null, N-U-L-L, hypothesis. The assumption that nothing is happening, that there's no effect, that your prediction is wrong. You assume innocence. And then you ask, is there enough evidence to reject that assumption? Is the evidence strong enough to convict? We'll talk about this much more when we get to hypothesis testing, but I want to plant the seed now. Statistical reasoning has a structural similarity to legal reasoning. You start with doubt, you demand evidence, you don't convict without proof beyond a reasonable doubt. Any idea, any prediction, any hypothesis is innocent until proven guilty, meaning it's innocent until we build up statistical evidence in support of or against it. Okay. All right, let me step back and address a question that's probably, hopefully, on some of your minds. That was my computer cord again. You've seen these examples. You see the statistics can help answer interesting questions, but why should you study statistics? What's the point for your life? And here's my answer, and I think it's the most important thing I'll say in this section. You need to be a critical consumer of information, okay? Even if you're not going into a research field, a statistics field, or even into psychology, you should be able to be critical of statistics and information that is reported to you. It'll happen throughout your entire life. It probably happens more than you're even aware of. Every day you're bombarded with claims. The news tells you that studies show this, research proves that. Politicians cite statistics to support their positions. Advertisers cite statistics to sell you products. Social media is full of, infographics and charts and numbers that, supposedly tell you something important. Most of these claims are somewhere between misleading and absolutely false. Okay? Sometimes the underlying research is flawed. Sometimes the reporting distorts the findings. Sometimes the statistic is technically accurate, but creates like a false impression of how important it is. Sometimes it's completely made up. Statistics are a little bit dangerous in that people will trust them at face value, or people don't have the skill set to interpret what statistics really means. So if you don't understand statistics, you're at the mercy of whoever is making these claims. You have no way to evaluate them. You just believe whoever sounds the most confident or whoever confirms what you already wanted to believe. If you do understand statistics, you can push back. You can ask, how big was the sample? How was the study designed? What's the effect size? Has it been replicated? What are the alternative explanations? What are they not telling me? You become an independent thinker rather than a passive recipient of information. Okay. So let me tell you something. We live in an age of misinformation, right? Everyone has access to platforms. Everyone can spread claims. The volume of information is overwhelming, and most of it is junk. Okay. The only defense is the ability to think critically, and statistical thinking is a big part of that. It's the skill of asking, where does this claim come from? What evidence supports it? How strong is that evidence? What would I need to see to change my mind? This is not just an academic exercise. This is survival in real life. This is how you navigate reality without being constantly manipulated. Okay. Now, having said all that, I need to balance it with an equally important point after I take a sip of lemonade. Statistics have limitations. They can be misused. They can mislead. Just because something is expressed numerically does not mean it's true or meaningful or important. So let me show you what I mean with some examples. Examples I like to call ridiculous statistics. Just for humor's sake, let me run through a couple to drive the point home, okay? Here's the first one, okay? Oops. Give yourself a minute to think about this. On average, this is true, humans have one breast and one testicle. Is this statistic true? Yeah, in a sense, yes. If you add up all the breasts in the world and divide by the number of people, you get approximately 1 breast per person. Same with testicles. The arithmetic is correct. That's true. Is this statistic meaningful? Absolutely not. It tells you nothing useful about anyone. It doesn't describe any actual human being. It's a mathematical artifact that results from averaging things that shouldn't be averaged, okay? So a statistic can be technically true and still be completely useless or misleading. When you see an average, a mean, you need to ask, is this average meaningful? Does it represent something real, or is it just nonsense, a nonsensical combination of different things? If someone tells you the average income in a room, that might be useful, but if one person in the room is a billionaire and everyone else is broke, the average is meaningless. It doesn't describe anyone's actual situation. The outlier, the billionaire, has distorted the statistic beyond recognition, okay? So statistics are tools, and like any tool, they can be used well or badly. Hammer's useful for driving nails. It's not useful for cutting wood. The mean is useful for describing symmetrical distributions. It's misleading for skewed distributions or mixed populations, okay? So knowing when to use which tool is part of statistical literacy. So we haven't even gotten to means yet. That's a few topics from now, but you've probably encountered averages before, and now you know, do we trust the average that's being reported to us? Sometimes we shouldn't. Sometimes it's not appropriate to use such a statistics to describe, a certain phenomenon, okay? Here's another example. And this one is important because it illustrates a concept we'll discuss throughout the course. A correlation is a co-relationship between variables. You've maybe heard the term used in everyday language or in your other psych classes. People will say there's a correlation between this and that, but often they use it without really understanding what a co-relationship is. So let me show you on a graph. On one axis, we have the number of people who drowned in swimming pools in a given year. On the other axis, we have the number of films Nicolas Cage appeared in that year. Okay. So look at this. The lines track each other almost perfectly. When Nicolas Cage makes more movies, more people drown in pools. Okay. When he makes fewer movies, fewer people drown. We need to arrest him. Okay. The correlation coefficient, the number that quantifies the strength of the relationship, is very high. You can see it there under the title. In technical terms, this would be what we call a strong correlation, a statistically significant correlation. In a research context, that's usually a pretty exciting finding. So what should we conclude? Should we arrest Nicolas Cage, ban him from making movies to prevent drowning deaths? Okay, obviously not. This is nonsense. Nicolas Cage's filmography has nothing to do with pool drownings. The correlation is completely spurious, a statistical coincidence, not a meaningful relationship. And yet, if you didn't know better, if you just looked at the numbers, you might be fooled. The correlation is real. The statistics are real. They are correct. But the interpretation is absurd. This is why statistics alone are not enough. You need to combine statistical analysis with substantive knowledge. You need to ask, does this relationship make sense? Is there a plausible mechanism? Could there be a real connection? In this case, the answer is obviously no. But in many cases, it's less obvious. There are plenty of correlations that look meaningful but aren't. And there are plenty of correlations that look spurious, coincidental, but are actually important. The skill is learning to tell the difference, and that requires more than just running the numbers. This brings me to one of the most important principles in statistics, so important that I'm going to say it slowly and clearly, and we'll return to it again and again throughout the semester, okay? Correlation does not imply causation. If two things are correlated, if they tend to go together, that does not mean one causes the other. It doesn't mean there's a causal relationship at all. They might both be being caused by something else. They might be related through a complex web of factors. They might be coincidentally linked with no real connection. Let me give you a more realistic example than Nicolas Cage, okay? This is also true research. This is 100% true. There's a correlation between ice cream sales and drowning deaths. In months when more ice cream is sold, more people drown. Does ice cream cause drowning like Nicolas Cage movies do? Obviously not. Okay, the explanation is both are caused by a third variable, hot weather. When it's hot, people buy more ice cream. When it's hot, people go swimming more. When people swim more people drown. The ice cream and the drowning are both effects of the same cause, but there's no direct connection between them. This is called a confounding variable, a third factor that explains an apparent relationship between two other things. And confounding variables are everywhere. They're one of the biggest challenges in research. When you see a correlation, you have to ask, could there be a confound? Could there be a third variable that explains this? This is especially important in psychology, where we often can't do true experiments. We can't randomly assign people to experience trauma to see if it causes depression. We can't randomly assign children to different parenting styles to see which produces the best or the worst outcomes. We're stuck with observational data, correlations, and we have to be very careful about drawing causal conclusions, okay? We'll talk about this later in the course. It's our second to last topic, in fact. But for now, just remember, when someone says X is correlated with Y, don't immediately assume X causes Y. It might, or something else might be going on. Let me go back to this, okay? Let me tell you about something darker about statistics, something that's not usually taught in introductory courses, but that you need to know. There's a saying in statistics, Mark Twain actually said this, if you torture data enough, it will confess to anything. What does that mean? It means that if you have a data set and you want to find a particular result, you can usually find it. You run enough analyses, you look at enough subgroups, you try enough variations, eventually, by chance alone, something will come out statistically significant. Okay? Data is rich with information, and you can make a statement about almost any data set, but that doesn't mean the statement is meaningful or true. This is one of the reasons psychology is in trouble right now. You might have heard of something called the replication crisis. Okay? The discovery that many published findings in psychology don't actually replicate when other researchers try to reproduce them. A lot of those failures are because the original findings were spurious. They were the results of torturing the data until it confessed. So this isn't always fraud. Often it's unconscious or accidental. Researchers have hypotheses they believe in. They want those hypotheses to be confirmed. They have careers writing on publishing positive results. And so they run analyses different ways. They drop outliers. They try different measures until they find something that works. They're not lying exactly. They're just flexible, okay? And that flexibility corrupts the literature. Okay. This is why pre-registration matters, deciding in advance what analysis you'll run, so you can't torture the data after the fact. Okay? This is why replication matters, seeing if findings hold up when other people try them. This is why transparency matters, sharing your data and methods so others can check your work. And this is why you as a student need to understand these issues. You'll be reading research throughout your career. You need to be able to spot the signs of data torture, and you need to be skeptical. Okay? Remember what I said at the beginning about the recovered memory therapists? They weren't measuring properly. They weren't comparing outcomes. They weren't testing their assumptions, and they destroyed families. Okay? The stakes are real. This is actually an important class. I want to close this lecture by zooming out and talking about something that isn't usually discussed in statistics courses, but I think it's essential. It's what ties everything together. Statistics is not just a technical skill, it's a moral practice. When you collect data, analyze it, report results, you're making claims about reality, and those claims will be believed. They'll influence what people think, what they do, what policies they vote for, what treatments they receive. If you're sloppy, you spread misinformation. If you're dishonest, you corrupt the search for truth. If you're careless about the limitations of your conclusions, you mislead people who trusted you to know what you were doing and to be honest. And the stakes can be high, life or death. Medical research influences treatment decisions. Psychological research influences therapeutic practices. Social science research influences government policy. People's lives are affected by what researchers claim to have found. So when you learn statistics, you're not just learning techniques, you're taking on a responsibility. The responsibility to do it right. The responsibility to be honest about what you find. The responsibility to acknowledge uncertainty instead of hiding it. Okay? There is a Russian writer named Solzhenitsyn, wonderful writer. He documented the Soviet prison camps under communist USSR. And he wrote something in his book, The Gulag Archipelago, which you should read. And I often think about this. He said, the line separating good and evil passes not through states, nor between classes, nor between political parties either, but right through every human heart. Okay, right through every human heart. You have the capacity for evil. You do. I don't know you individually, but I know you're human. And that means you have the capacity to do terrible things while believing you're doing good. Everyone does. That's the human condition. That's what the stories about lobotomies and recovered memories illustrate. You can go wrong. You will be tempted to go wrong. And the temptation won't feel like temptation. It will feel like righteousness. And the only protection, the only partial protection is discipline, is subjecting yourself to constraints, is building structures that will catch you when your instincts fail, is checking your beliefs against reality over and over and over. That's what science is supposed to be. At its best, that's what it is. A community of people who have agreed to hold each other accountable, to check each other's work, to demand evidence, to not let claims stand just because they sound good or feel right or come from someone with authority. And statistics is the language of that accountability. It's how you make your claims precise enough that they can be tested. It's how you quantify uncertainty. It's how you distinguish between I have strong evidence for this and I'm just guessing. Okay. There's another angle on this that I want you to consider. Okay. Competence is a moral virtue. It's not just an intellectual accomplishment. It's an ethical requirement. Because here's the thing, you can't navigate the world properly if you don't perceive it accurately. You can't help people if you don't understand what's actually wrong with them. You can't make good decisions if your map of the world, of the mind, of whatever, doesn't match the territory. And so when you deceive yourself, when you let your biases run unchecked, when you're not competent, when you don't understand things, when you trust your intuitions over data or don't even know the data, when you let wishful thinking masquerade as knowledge, you're not just making intellectual errors, you're compromising your ability to act properly in the world. You're making yourself dangerous. The lobotomists were dangerous. The recovered memory therapists were dangerous, not because they wanted to hurt people, but because they didn't know what they were doing, and they didn't know that they didn't know. They were confidently incompetent. And confident incompetence in a position of power and trust is one of the most destructive forces there is. Now, let me make this personal, because this isn't just about historical disasters. It's about you right now in this room. You're in school to become competent, not to get a degree, not to check a box, not to satisfy some requirements so you can move on with your life. You're here to learn, to actually acquire the ability to do something valuable in the world. And if you're not learning, if you're just passing, then you're participating in a kind of fraud. You're accepting credentials you haven't earned. And eventually, maybe not next year, maybe not in 5 years, but eventually someone will trust you based on those credentials, and you won't be able to deliver. You'll be the lobotomist who doesn't know what he's doing. You'll be the therapist implanting false memories, not because you're malicious, but because you skipped the part where you were supposed to become competent. Think about that. Really think about it. Okay? And this brings me to something I need to address directly, because it's relevant to your situation in a way it wasn't relevant to students 10 years ago. Artificial intelligence, ChatGPT, Claude, whatever tools are available to you. Here's the thing about using AI to do your work. It's not cheating in the way that copying from a classmate is cheating. It's worse. It's outsourcing your own development. It's paying someone else, something else, to do your push-ups and then wondering why you're not getting stronger. When you ask AI to write your paper, to solve your statistics problem, to explain something you should be struggling with yourself, you're not saving time. You're stealing from your future self. You're arriving at the credential without taking the journey that the credential is supposed to represent. And the journey is the point, the struggle to understand. That's what builds the neural architecture. That's what creates the intuitions that you're going to need later on. That's what makes you actually capable rather than someone who can mimic capability. I'm not naive. I know these tools exist. I know you can use them. I know that in some contexts, using them intelligently is actually a skill worth developing. But there's a difference between using a tool to extend your capabilities and using a tool to replace capabilities you never even developed in the first place. So like a carpenter who uses a power saw is still a carpenter. Someone who has a robot build the house while they just sit there and watch isn't a carpenter. They're just someone who owns a robot. You're here to become the carpenter, to develop the judgment, the understanding, the ability to know when something's gone wrong and how to fix it. If you outsource that development, you'll graduate with a degree and no actual competence, and then you will be exactly as dangerous as the lobotomist. Someone with credentials, with authority, with people trusting them, and nothing real underneath. That's not just an intellectual failure, it's a moral failure. You owe it to the people who will eventually depend on you, your future clients, your patients, students, employees, whatever, to actually know what you're doing. You owe it to them. So when I tell you that competence is a moral virtue, I'm not speaking abstractly. I'm talking about whether you do the reading, whether you struggle with the problems before looking up the answers, whether you sit with confusion until it turns into understanding, whether you earn what you claim to have. That's the foundation. Everything else in this course builds on it. So, statistics, it's not just math. It's a discipline. It's a corrective. It's a set of tools for keeping yourself honest when every instinct is pushing you toward comfortable self-deception, okay? Let me pull together what we've covered today, okay? The human mind is unreliable. We suffer from confirmation bias, the availability heuristic, pattern recognition errors, and many other systematic flaws. These aren't occasional mistakes. They're features of how our mind works, and they can lead to catastrophic errors, as the history of psychology demonstrates, okay? Statistics exist to protect us from ourselves. It's a set of formal procedures that constrain our tendency towards lying to ourselves, towards self-deception. It forces us to measure, to compare, to quantify uncertainty. And statistics are numbers used to describe data from a sample, okay? They're summaries, simplifications of complex information is something that you can understand. Population is everyone you're interested in making claims about. A sample is a subset you actually study. Almost always you work with samples and then infer back to the populations. We use different symbols for populations and samples. Capital N for population, lowercase n for sample, mu for population average, x bar for sample average. Parameters describe populations, statistics describe samples. There are two branches of statistics, okay, descriptive and inferential. Descriptive summarizes your data. Inferential helps you draw conclusions that go beyond your data. Statistics helps us answer empirical questions about the world that can be addressed with evidence, but statistics don't give certainty. They quantify uncertainty. We've seen examples of research. Attractiveness affects jury verdicts. Lawyers are more competitive. But in each case, we had to think critically about what the results mean and what alternative explanations exist. Okay. Statistics have limitations. The mean of a mixed group can be meaningless. Correlations can be spurious. Causation can't be inferred from correlation. Data can be tortured into confessing anything. And another thing we covered is being a critical consumer of information is essential. So statistics are everywhere and most of them are used to mislead. Your only defense is understanding what the numbers mean and what they don't mean. Okay. Statistical practice, this is another thing we covered, is a moral enterprise. When you make claims based on data, you're responsible for getting it right. Sloppiness and dishonesty have consequences far beyond the academic and your grades. Okay. Competence is not just an intellectual virtue, it's an ethical one. All right, looking ahead. In our next topic, we're going to dig into the foundations, variables, and measurements. This might seem basic, but it is crucial. Before you can do any statistics, you need to measure something, and measurement is harder than it looks. Okay, what does it mean to measure intelligence? Depression, happiness, personality, attractiveness. We'll talk about different types of variables. We'll talk about different scales of measurement and the challenges of operationalizing abstract constructs. We'll see that the choices you make about measurement determine what conclusions you can draw. Remember what I said about the responsibility of precision? So it starts with measurement. If you define things loosely, you can make evidence that supports any claim. If you define things precisely, you constrain your interpretations to what the data actually supports. Okay, but that's for next time. Okay, so between now and next class, I want you to do something. Okay. Notice statistics in your environment. They're everywhere, in news articles, in social media, in advertisements, in conversations. Pay attention to the claims being made. Ask yourself, how do they know that? What's the sample? What's the population? What are they not telling me? What are the limitations? Start developing the habit of questioning, not being cynical and just dismissing, but genuine questioning. Most statistical claims aren't lies, but they're often incomplete, misleading, based on weaker evidence than they imply. Your job as someone learning statistics is to become harder to fool, not paranoid, just appropriately skeptical. Okay, aware that numbers can deceive, that your intuitions are unreliable, that the truth is usually more complicated than just the headline. Okay, that awareness is the beginning of statistical thinking. Okay, and statistical thinking is one of the most valuable intellectual skills you can develop. It's also one of the most important moral commitments you can make. A commitment to pursue truth, to resist self-deception, to be honest about what you know and what you don't know. To not claim more than your evidence supports. That's what this course is about. Not just techniques, but character. The kind of person who can be trusted to get things right. Okay? That's it for today. I'll see you next time. And it's perfect timing because I have a brand new baby kitten who is telling me that it is time for her to have a bottle of milk. So I'll see you next time. Bye.